Hey everyone, I'm Ashley. I'm a junior at the University of Connecticut and I'm majoring in applied math, Chinese, and computer science and engineering.
My name is Jonathan Montag. I'm currently a senior at Hofstra University studying computer science. Our research was on quantum deep learning for binary classification, and we were mentored by Dr. Ying Mao and Samuel Stein from Fordham University.
In classical computing, information is stored in bits. Singular bit can only be represented as a 0 or a 1, so calculations with classical computing are deterministic, and this means that repeating the same input would give us the same output. But in quantum computing, information is stored in quantum bits, which are also known as qubits, and these qubits can be represented as a 0 or a 1, or 0 and 1 simultaneously, and that is due to superposition. So calculations in quantum computing are probabilistic, which means that there are multiple possible outputs from the same input. Quantum computers can represent 2 to the power of n states with n qubits, meaning their power scales exponentially compared to classical computers. A variational circuit is a trainable quantum circuit that is parameterized by data values. Classical optimization algorithms can be used to train these circuits by making queries to a quantum device. So the goal of this research project was to train a circuit capable of classifying handwritten digits.
In order to train the quantum circuit to be able to classify images, we need to complete the following steps. I'll go into more detail on the inner workings of these steps in the later slides, so for now I'll just give a high-level overview. First, we prepare our image data, and then we encode that data onto the qubits in our circuit's input layer. Once this is done, we're ready to train our quantum circuit, and lastly, all we have to do is test the circuit so we can see how well it performed. For data preparation, I first downloaded 60,000 handwritten digits from the MNIST dataset. The MNIST dataset is just a large dataset composed of 60,000 handwritten digits that are represented by 28 by 28 matrices of grayscale values from 0 to 1, where 0 is going to be the lightest color of white and 1 is going to be the darkest where it's black. The original dataset has digits 1 through 9, however, since we're only interested in binary classification, I discarded every single digit that's not a 3 or a 6. Now we're only left with a balanced dataset of 14,032 images, where half of those images are 3s and the other half are 6s. After this, I then split the data again, so we can use 12,032 of the images for training the model, and then we leave the other 2,000 images for testing the model. Lastly, I take the original images and downscale them from 28 by 28 pixel images to an 8 by 8 pixel image. The images below show a 28 by 28 image of a 3 being downscaled to an 8 by 8 pixel image. Although this makes the picture more distorted and could possibly decrease our accuracy score, this is going to drastically increase our computation speed since we only have to work with 64 pixels from the 8 by 8 image rather than using 784 pixels, which we would have in the 28 by 28 original image. Since we're working with 8 by 8 pixel images, we're going to have a total of 64 features for training our model. In order to encode the image data onto our circuit's qubits, we first need to transform the 8 by 8 matrix into a one-dimensional vector of size 64. These 64 features can be encoded into just 6 qubits. The amount of qubits needed to hold our image data is obtained by calculating the upper bound of log base 2 of the amount of features we have. Therefore, in our case, we need 6 qubits since log base 2 of 64 is equal to 6. This process allows quantum computers to use exponentially less space than a classical computer would need to store this amount of data. Once our data is pre-processed and our qubits are encoded onto an input layer, we can build our quantum circuit. Using Qiskit, which is a Python library for quantum computing created by IBM Research, we can put together our circuit and visualize it. The quantum circuit uses RY gates, which will rotate the qubits through the y-axis by the theta value, which is shown below the RY in the image below. The RY gates with vertical lines coming off of them are called controlled RY gates. These gates have their own parameters as well and are used to entangle the circuit's qubits. The circuit's gates are originally set to be random values between 0 and pi, which is very similar to how a classical neural network's weights would be initialized to random values at first. Our circuit also uses one classical bit, so we can read our data from the circuit and record an output which will either be a 1, representing the model's prediction is that the image is a 3, or a 0, showing that the model's prediction is that the current image is a 6. Since quantum computers are probabilistic, the same input can have different outputs. Because of this, if we only run the circuit once, then we can get a random value that's either 0 or 1, which may not actually be indicative of the circuit's real prediction. To fix this issue, all we have to do is measure the circuit many times, and then we can count how many times its input is a 1, and then count how many times its input is a 0. And then using these counts, we can transform this into a probability. So for example, if we run this circuit 10,000 times, and the circuit outputs a 0 9,000 times, and then a 1 1,000 times, we could say that the model's prediction is that there's a 90% chance that this image is a 6 and a 10% chance that the image is a 3. To train our quantum circuit, we use mini-batch gradient descent. Again, just like how a classical neural network needs to change its weights in order to learn, our quantum circuit also needs to shift its parameters in order to learn. With mini-batch gradient descent, we're going to first split up our data into 64 batches of images from our training set. We will then loop through this batch for each parameter in our circuit and compute the parameter shift rule, which is going to tell us how much to shift our current parameters gate by and in what direction. To find the value to shift our current quantum gate by, we first increase our current gate's value by a value of pi over 2, and then run the circuit 8,000 times over each image so we can get all the corresponding probabilities for our current batch. Using these probabilities, we can compute the average loss over the batch of data using the binary cross entropy loss function. We then do the same exact thing, but instead of increasing our value by pi over 2 for the current gate, we decrease our value by pi over 2. Once we have these two average costs, we can subtract our second cost from our first and divide that number by 2. Lastly, we multiply this number by a learning rate and shift our gate's value by the final result. After completing this process for each batch of data, our circuit will be finished training and we can test our results. After each batch is completed, we compute the accuracy score for the training set and the testing set so we can see how well our model is doing. This is also going to help us ensure we are not underfitting or overfitting our data. The images below show an image on the left where a model is underfit since too many predictions are incorrect, and the image on the right shows a model where the model is overfit since it is very accurate, however it's not going to generalize well to new data. Overfitting and underfitting your model could be caused by many factors such as training for too long or not training your model long enough. As you can see, the model in the middle does miss some predictions, however it seems to be a good fit because it gets many predictions right and will generalize well to new data. When testing our model on 2,000 unseen images, the model was able to correctly classify 95.35% of them, which is very competitive when compared to other similar research. Below you can see two graphs. The graph on the left shows how the model's accuracy increases over each batch during training, and the model on the right shows how, over each batch, the model's loss slowly decreases.
For future research, we can extend our variational quantum circuit capabilities to be able to handle multi-class classification.
For future research, I would like to look at different optimization methods, such as quantum natural gradient descent. This is a separate form of gradient descent that is specifically meant to traverse the quantum landscape. This will help us find minima of our cost function much quicker. This will also help us reduce our training time and can also potentially increase the model's accuracy to over 95%.